So,
I think, well, you can
should
start
get
now.
started. Yeah.
You can decide where you want to stop during.
Yeah.
You want to take more time to either the lecture or the hands-on. So
Okay.
feel free. You have 2 hours.
Yeah.
Maybe so.
Okay. Is this on already? Yeah.
That should be on. Yes.
These also? Hello?
Well,
Okay.
that's okay. No.
I don't know.
No. Well, if there is too many interference, just switch it off.
Mics are on?
You can maybe put this here below in order to avoid the interferences. That's fine for.
It's fine.
Okay.
Okay. Okay, welcome back. I hope you had a good afternoon. And so, after skiing, now being tortured with a dry subject like gravitational force calculation is pretty cruel. But I'll do it anyway. Maybe you find it relaxing. Who knows? So the plan is now that for the first hour or so until 6, I'll talk about this lecture 2. Gravitational n-body methods. This is relatively computationally oriented, so I want to tell you a little bit about the methods that we have at our disposal. Maybe a little bit about initial conditions also. And then I stop, and then in these hands-on sessions we can try to do some simulations together, either with the gadget code or with the Athena code, or both, depending on what you prefer. That's the plan now for this afternoon. So this morning I already talked about the complexity of the gravitational force calculation, right? It's an n-squared problem. And unfortunately it is an n-squared problem. To do this correctly, to calculate the forces for n particles exactly, you have to bite the bullet basically and have to calculate these n-squared half terms. So that's, in a sense, kind of seems to be bad news. And it is indeed bad news for people who are doing collisional dynamics. Star cluster calculations, so where you often have to have relatively precise forces. So to a large extent, the reason why these people have still not reached very large particle numbers compared to cosmology is because they have to attack this force calculation more or less exactly, or at least with far fewer approximations. The question then is, do you really have to do this exactly, or are approximate force calculations sufficient? Fortunately for galaxy formation, we are in a situation that the answer here is a sound allowed yes. It is fine. We don't have to get so exact gravitational forces, but this is fine provided the force errors that we then invariably have are kind of random, and they should be small enough. The randomness means because the n-body force field is noisy anyway, small random errors in the forces are actually irrelevant. They only very insignificantly reduce the relaxation time further. And so, for example, if you have a 1% random error on the forces, normally in a realized system, the relaxation time will be modified by 1%. That's totally acceptable. What's harder to guarantee is that these errors are really random. If you have strong systematic force errors, that's much more problematic, right? And we would like to avoid those. Now I want to first talk about the particle mesh algorithm. This is a standard technique that you should all understand how this is working. Basically, here you try to solve Poisson's equation, and you view, first of all, that Poisson's equation can really be integrated, or the solution to it can be written as a convolution of the density field with some Green's function. So this Green's function encodes the response of a density at coordinate x. Actually, there's an x prime here missing. So we have at density at coordinate x prime, we have some density, and the Green's function tells us what potential this creates at some other point x. So you actually all know what the Green's function is for Newtonian gravity then, because we know we can calculate potential with this integral over the mass distribution, where the Green's function is the 1 over r kernel minus g over the distance vector. So this would be in Newtonian gravity our Green's function. But when you have a convolution like this, you remember some mathematical theorems about Fourier transformations. If you go to Fourier space, if you Fourier transform the convolution, it turns into an algebraic multiplication. That is, this equation Fourier transform will be the phi hat is the Fourier transform of the potential, is then the Fourier transform of the Green's function times the Fourier transform of the density field. And the cool thing here is really that this is a pure multiplication of these two functions, which is much easier to calculate, obviously, than doing such a convolution in real space. So somehow we would like to exploit this convolution theorem. The way to do this would then be the following. You have the following idea. Let's solve for the potential in these steps. We take the density field. We need to obtain this somehow. We Fourier transform it forward to obtain this rho hat. And then we multiply that with the Green's function, g hat. What we obtain is phi hat. And then we need to apply the inverse Fourier transform to get from phi hat back to the potential. And indeed, this is what the particle mesh method does. And in detail, there are basically 4 steps. What I left out is, one is to get the density field in the first place, because we start off with particles. So we have to make a density assignment of some kind to get a density field. Then we calculate the potential with these 3 steps. From the potential, we'll still have to calculate something like a force. So somehow, from the potential, we need to get to a force field. And once we have a force field, we can maybe assign forces to particles. So there are a few more little details in the particle mesh scheme. I want to briefly go through those. So density assignment means that you have some sort of mesh, but you're really starting out with your dark matter particles. They are in the same space as the meshes, and you would like to map the dark matter mass that's in the particles to this grid. There are different choices for this. For example, you can assign basically the particle kind of a shape function, here S in this equation, and then calculate something like the overlap of this shape with a cell. Okay, this is how you would assign, how you would spread the mass of the particle onto this mesh. Mathematically, this would look sort of like this. And this assignment function is actually, this can be viewed also as a convolution of the assignment kernel, basically with something like the cell size. And now, and then the density on the mesh is the sum of the contributions of each particle as given by this assignment function. Now this assignment functions, and this is useful to know what the normal language for this is. There are some kind of standardized ones that are often employed. And they come in different orders. The simplest assignment function is if you give this particle kind of the shape of a Dirac delta function. And if you do that, if you give it the shape of a Dirac delta function, that means that when you do the convolution of a cell size with this shape, the particle will be either completely inside a cell or not. Right? So this is essentially what this does, and that's why it's called nearest grid point assignment. You will put all the mass down to the cell in which this little point, this little dot, this infinitesimal Dirac delta function really lies. That's why this is called nearest grid point assignment. And that also means that the support of a particle here is exactly one cell. Right? Now the next higher order assignment function is what's called a clouds in cells assignment. Here you give the particle shape that's equal to a cube, the cubical size of one of your mesh cells. And once you put down now this cube and move it over the grid, you will see that it will overlap typically, of course, in 3D with 8 of the mesh cells to various degrees. And exactly the degree of this overlap will determine how much mass you assign to each of these 8 cells. So the response then, or the density field that you get from a single particle will then be, this corresponds to a piecewise linear force that you eventually get. We'll see this later because the force reacts that you get from this density field to a small displacement of the particle. And the force field will be piecewise linear from such a density field because you integrate this again. And then there are higher order kernels like the triangular shaped clouds, where you essentially give a shape function that is like a little pyramid, and that will generally overlap, have a support of it's a base length of I think 1.5 cells, or is it 2? Forgot. In any case, it will overlap in general with 27 cells in 3D. These higher order assignments, they create smoother density fields, which has various advantages, right? But it's also computationally more expensive. It is, of course, a lot easier to bin down particles onto single cell instead of spreading every cell over a support of 27 cells. And that's a general trade-off that you have to make. For higher smoothness, you have to have a higher support. The stencil of the density assignment will be larger. This is computationally more costly. You get then a smoother result. Whether you really need this or whether it's overkill depends on the application. Anyhow, these are the basic techniques to create the density field. Once you have the density field, you go through the steps that I showed you, that you Fourier transform and you multiply with the Green's function, Fourier transform back. And then you get the potential this way. With the potential, you have to do something similar. The potential is now on a grid. If you need that potential values for the particles or the forces, you first need to transform the force. You first need to transform the potential field to a force field. This you do generally by finite differencing. So somehow we would like to take this potential field. This means essentially that on such a grid, we maybe have a potential value at all cell centers or at the corners. But we would like, for this particular particle sitting here close to a corner of a cell, we'd like to know its force. And that somehow you have to infer from the surrounding values of the potential. What you first do is you make an estimate of the derivative of the potential. For example, via finite differencing, you take such a finite difference formula. This is what, for example, would be the force in the x direction. You would like the partial derivative in the x direction, and typically would do this by differencing the left and the right cell around a given cell. Divide that, take the difference, divide this by 2 times the grid spacing. That is a derivative estimate. That's second order accurate in this case, which you see by, for example, Taylor expanding that. There are also higher order accurate schemes. You can go to 4th order. Then the so-called stencil will be larger. For a 4th order accurate finite differencing, you will not only need the 2 neighboring cells, but typically, say, 2 on the left side, 2 on the right side. Combine them like this, and then you get a higher accuracy in the force, smoother force, again at the expense of a higher computational effort. And you have to see whether this is worthwhile or not. Once you have such a force field, you then need to interpolate to a particle. And this basically means that you make a linear combination of the forces that you see on the grid around your particle. In this linear combination, one can show that in the particular case of the particle mesh algorithm, the assignment kernel here needs to be the same that you used for putting down the density. If you do that, then you avoid self forces that could occur. Right? You can prove this relatively easily, that if you do that, then there should not be any self force, and the forces are, in particular, they are antisymmetric between 2 particles. Good. So what are the advantages and disadvantages of this simple particle mesh scheme? This came originally from plasma physics to astronomy, basically. The first cosmological simulations were done with this, with plasma physics codes, actually, by George F. Staffio and Simon White and Carlos Frank and others. The advantage of this is a high speed and the extreme simplicity of this. You basically can code such a thing, probably if you're very experienced, probably in 1 afternoon or so, you can write such a code today. So it's very easy and relatively fast. The downside of this is that the spatial force resolution is obviously limited, namely to the employed mesh size. Also, the force errors are somewhat anisotropic on the scale of the cell size. This is, however, not a very serious one. and can also be overcome by force shaping measures. But this limited resolution is a very serious problem. Especially in cosmology, we have density contrast. The centers of galaxies, their densities reach 1 billion or so, larger overdensity relative to the background density. So this is extremely nonlinear there. And the mass is assembling in a tiny fraction of the total volume. So if you start out with a homogeneous density where such a mesh is appropriate, you have simply no chance to use a fine enough mesh that's uniform everywhere in the beginning to capture this dynamic range. So that basically means that PM only is only useful for a couple of really rare applications. It's still used in the field though sometimes. So somehow we want to increase the dynamic range. And the widely used technique for this, that is also a relatively old one, is the so-called particle-particle-particle mesh scheme. And here the idea is essentially that we would like to supplement the particle mesh force, which is sort of limited to the scale of the mesh, with a direct summation short-range force. With a direct summation short-range force at the scale of the mesh cells. And then you can maybe hope to get a much higher dynamic range. So basically this means if, this is already the next scheme, adaptive PQM, if all the particles fall into one cell, or not all the particles, if there are a bunch of particles falling into one cell, you then do a direct summation just for the neighbors in the same cell. That way you can enlarge the dynamic range. And that is actually, for a limited range, is working quite well. But it has the obvious drawback once the clustering becomes strong. If there are very many particles in a cell, you're back to the original problem of the n-squared algorithm, right? It just does not scale and it becomes very slow. And then people have invented schemes to maybe place two nested meshes like this. This was by Hugh Couchman in the adaptive PQM code, where certain refinement levels or secondary meshes were placed on clustered regions, so to avoid this problem. So you then have multiple levels of the particle mesh algorithm to reduce the clumping inside a cell, which then still needs to address with particle-particle techniques, direct summation techniques. It's also possible to do away with this Fourier transform business completely. And you can solve the potential also in real space directly, not using essentially convolution technique in Fourier space, but rather using a relaxation scheme where you, for example, use an estimator for essentially for the Laplacian of a given guess for the potential. If you have the potential guessed on the grid somehow, then you can improve this guess by an iterative formula like this. This is basically just, in a sense, this is a finite difference representation of the Laplace operator and the Poisson equation. And with this, you will actually converge by repeatedly applying such a formula, will converge to the real potential. And that is then a real space relaxation technique, avoiding Fourier transform business. So if you have a gigantically large homogeneous mesh, this technique is normally, if you apply it naively like this, will normally be slower. It's because this updating will basically very quickly give you, on small scales of a few grid cells, any error that exists there will be eliminated really quickly. But if you have a long-range error, it will take a long time until this goes away. Because, in a sense, whatever the error is, you will only locally smooth something out with this sort of operator. That would then imply a relatively slow convergence. And what, however, multi-grid methods do, and I will probably come back to this later in the week, they use a clever idea that you can use a hierarchy of meshes to avoid this problem. And what these techniques do in a sort of inverse, they take this fine mesh and first of all restrict this to a coarser mesh, and then maybe yet to a coarser and coarser mesh until you have only a couple of cells. You then iterate the two solutions on large scales, and you propagate this new solution backwards down to the finer meshes. And this way, you overcome this bottleneck of a slow convergence of the large-scale error. And you can then, the optimal case, these multi-grid techniques are also very fast and quite flexible, as we'll see. They are, because everything's working in real space here, they can more easily be adjusted to varying resolution in space. While the Fourier mesh, the Fourier technique, basically is then one that has, at a given level, a uniform resolution always. So examples for actually these real space solvers, they are used quite a lot in cosmology today, in Ramses, for example, the ART code, MLAPM, and probably more. Sometimes this is also combined, this relaxation technique with Fourier techniques. There are also combinations are possible. For example, you could use the Fourier technique on the largest grid, also partially to avoid this issue that long-range errors die out slowly. Now let me come to tree algorithms. That's also a real space technique. And tree algorithms are also very widely used. And here you do something different. You entertain the concept of a hierarchical multipole expansion. So you use what's called often a hierarchical tree algorithm. So how does this work? Basically, if you imagine you have a bunch of points like these, when you are, I mean, this is still a relatively small collection of points, obviously, but suppose you have this group of mass points over there, and you would like to calculate the force somewhere down here on the left, then you could, of course, sum over the individual forces created by these points up there. That would be the direct summation approach, would give you the exact result. But you notice from calculating, say, the gravitational field of the moon, that this is crazy, man. If you want to know what the force of the moon is, you don't sum over all its individual rocks or dust grains, right? You don't do that. Rather, you take one mass at the center of mass of the moon, and that's the monopole term of the moon, right? And that describes, if you're far away, just perfectly fine, its gravitational field. And that's the central idea. If you are far away, everything is a sphere. I'm a sphere if I'm far away from something. Turning into sphere with age as well, probably. Yeah, so that is what you do in multipole expansion, right? You have to you just have to consider the lowest order multipoles, and the tree algorithm tries to systematize that somehow, systematically decide for distant groups of particles. Instead of calculating each individual force, I just want to calculate one force for these particles, namely the force from the total mass of these points at their center of mass, for example. And this decision you have to make at every coordinate, what groups of points you want to consider. That means you somehow need systematically a grouping of the points. And that is, first of all, what the tree does. We want to create a hierarchical grouping of the points. And for this, there are different possibilities. The most widely used one is a so-called Barnes and Hart octree, or in 2 dimensions it would be quad tree. So you enclose the points, for example, here in a box like this, and you will subdivide the box into 4 daughter boxes in the middle, and you keep subdividing this until a box contains at most one particle. Then you end up at the leaf cell. So, and the tree is then sort of this structure, that you have a root node, say here, and this has 4 daughter nodes, and so on and so on, and down here the leaves of the tree hang off. Now, what do we do with this then? So here's it shown again. So suppose you have these set of points here at the level 0. You subdivide this, you get the level 1, and you keep subdividing. And notice here that, for example, this is a tree has only 4 levels. And at the deepest level, you normally will not store any of the empty nodes. It's not really necessary. But with this approach, you now have a hierarchical grouping. In fact, this is very similar to what in adaptive mesh refinement and some hydrodynamic codes is done. These are nested inside. So there is a sort of nesting in this octtree structure. Now we have groups, and for every of these groups, we would like now to calculate, first of all, we start out with calculating so-called multipoles. The multipole expansion, what is this again? Suppose I have such a group here of points, and I would like to calculate the potential down there. Then, well, we know how this is done. We just have to sum over all the mass points, and then we have the kernel, the Green's function is 1 over r minus xi. So this is the exact result. But now we can make an expansion. What do we expand? Well, we expand basically this 1 over r minus xi, and we rewrite this first of all and plug in here the center of mass s in this form. Right? I can put this in here and express this as r minus s. This is just the distance to the center of mass of the points, and then I have distances of the individual points to the center of mass itself. And now I would like to expand this here in the limit that the individual distances to the center of mass of these points are small compared to my distance to the center of mass. Right? In other words, I'm far away from the object. I'm seeing it under a small angle. If I see it under a small angle, I can then Taylor expand this denominator. For example, like this. And you know, you can get 1 over y. The y is here the distance to the center of mass. This will give me the monopole term. If you plug this in, this is just a Taylor expansion of this expression. If you plug this here in, you then get the so-called multipole expansion, and the lowest order term will be the total mass, because this you can then carry out the sum of the masses of the group divided by the distance vector from the point where you want to evaluate the potential to the center of mass. The next order term would be a dipole term, but the dipole term here, this is this guy, you will see that the sum over this will vanish. That's good. So the next order will always go away. That's because I've conveniently chosen my point of reference here as the center of mass. That's why the dipole will go away for the gravity part. Then there will be the octopole and furthermore higher order terms. Yeah, so once we have the grouping, we calculate the monopole terms, for example, the mass and center of mass and the quadrupole tensor for all of the groups. And then the resulting, for example, potential force approximation up to quadrupole order would be this term. Okay, this is the approximation for the potential for a single node. And the question then is, why is it now faster in any way, right? So the reason for this is now that you do a so-called tree walk, and the tree walk, yeah, I guess I have to go back to explain this with this sketch. So once we have calculated the multiple moments for all of these groups, when we now at a certain coordinate, we do a so-called tree walk. We look first at the root node of this tree, and we calculate this opening angle under which this node appears. And if this opening angle is small enough, in other words, if we think that the multiple expansion is sufficiently accurate, then we use it, and then we are done. We have accounted for all the force that's done from this mass. If the angle is still large, we have to subdivide the group and look at all its daughter groups. And we keep doing this, and you can then convince yourself that the number of groups you expect is something like log n, where n is the particle number. That means that the whole cost of the force calculation is done going down from an n squared to an n log n cost. And that's a huge saving. Now, there are other advantages to this tree algorithm because it has no intrinsic restrictions for its dynamic range. It makes this grouping automatically depending on the clustering, and the number of nodes is also roughly constant. So if you've moved the points around and you're creating complicated structures, then you just get the tree nodes where the mass is, and it will automatically adjust to whatever dynamic range there is. So it has a large geometric flexibility, this kind of scheme, which makes it convenient for many applications. Also, you can adjust the force accuracy in this particular algorithm. The force accuracy here is set by the opening angle that you use in this multiple expansion. If you make that smaller, means that you'll have to open the tree down to smaller nodes, and so you just do more work, but you get more accurate forces. So that's an adjustable parameter that you have to set by experience or depending on application to appropriate values that give you a useful compromise. Just the accuracy that that's needed to that you get away with without seeing any errors in your final results. That's basically what you want to achieve. And also the speed of this does only depend very weakly on clustering. Very unlike, say, p cubed m, which will be extremely sensitive to clustering. Geometrically flexible, I already said this. Now there are also variations of this. Sorry, this is a little bit faint. There's something called the fast multiple method. This tree idea can be expanded to not only doing a multiple expansion around sort of the source side of things, the mass that's creating the force field, but also at the target side, at the evaluation point of the force field. You make essentially an expansion on both sides, and that means that the tree walk is then not one-sided in a way that you have to repeat it for every single particle, but you simultaneously walk the tree on the source side and the sink side, and then you get forces between nodes and forces between particles and nodes also, and the total forces that are exchanged will then always be antisymmetric. So the huge advantage of this fast multiple method is that it's still faster than the tree algorithm. In fact, with this you can show that the cost for calculating all the forces now not n log n, but is actually now proportional only to n. So it's still better, and the prefactor is usually a few. So you can in principle be a few times faster with this. So it's very fast. And it manifestly conserves momentum. What this means is that the forces remain strictly antisymmetric. I mean, you know that when you calculate gravitational forces, they should be antisymmetric. It's one of Newton's laws. So that is related to total momentum conservation. If you, however, have an approximate force calculation scheme that may violate this at the level of the individual force accuracy if you have bad luck. And then again, if the force errors are systematic, if you're unlucky, your system might gain systematically momentum in whatever direction. And this can have, in some situations, disastrous consequences. Not necessarily so, but it's not particularly nice. This fast multiple method avoids that, and it, in principle, can have manifest momentum conservation. However, why is that not used more widely? I mean, Walter Dehnen, for example, has a code using that, which is also quite fast. But there are also serious disadvantages for this. And one is, for example, it doesn't really work very well with individual time steps. So if you have interesting problems, then they have a high dynamic range. And normally you can only do them with individual time steps. And this particular technique basically gives you the forces for all points, but not. If you want the force for just the millions of the points, it is unfortunately not a million times faster. But the one-sided tree algorithm is. If you want, you calculate the force for 1 point of 1 out of a million, and that is a millionth of the computational work. So that is more elastic in that sense, right? That's why this is an important point. Which, by the way, is always, I generally find that applied math people, they, for example, will tell you, oh, fast multiple method is the best algorithm, period. For them, the problem is solved, right? But they never, individual time steps, what is that? They just have no concept of this, right? They just treat the problem as, I have to calculate all the forces, this is the fastest algorithm for it, problem is solved. But sometimes there are situations where you want the force only for a fraction of the points. Unfortunately, actually, that's the generic application that we have in galaxy formation. Then it also is difficult to parallelize, but that can be overcome. Now finally, let me discuss a method that I myself like to use, which is the 3PM approach. And that kind of tries to combine what we heard about the tree algorithm with the particle mesh algorithm. And we go back here to the equation that was there this morning. We have the peculiar potential, we have the Poisson equation, that is what we need to look at in cosmology. We have the density minus the background density. That's the density fluctuation that's causing the seeding and sourcing the peculiar potential. And here on the right side, really what you have is here it's actually spelled out what you have in terms of periodic boundaries also. Something I haven't really talked about yet, but normally if you want to simulate a part of the universe with some galaxies in them, you find that you have to impose boundary conditions. And the most convenient boundary condition for the universe is to impose periodicity and use a cube. So you represent the universe as a periodic cube of some size L. And you only really calculating the fundamental box, if you want, of this periodic tessellation of the universe. But effectively, your mathematical model is now one of an infinite universe, which is good because we think the universe is infinite, actually, right? So that is why this is a convenient approximation, periodicity in some box size L. So you throw in your points, but then you have to replicate these points, strictly speaking. They are appearing not only in their fundamental box, but they should be periodically replicated. And then if you have a point of mass m, then this is described by Dirac delta function and its coordinate, but you have to subtract off the mean density that's associated with this point, which is 1 over L cubed here. So this is really what this looks, if you discretize this field by particles, this is what you have, Dirac delta field. Instead this is basically a gradation softened particle that is a little bit like a cloud of mass. So the idea now is that we can do this in Fourier space. We have seen this, but the problem is we can't find enough mesh to get all small scale details. But maybe we can separate off these small scales, and that's the idea in the 3M algorithm. So we go to Fourier space, and if you Fourier transform this equation over there, this one, due to the periodic boundaries, this becomes in Fourier space really simple. Because due to periodic boundaries now, the Green's function, remember this is the G hat, the Green's function of the Poisson equation, if it's the periodic Poisson equation, then the Green's function is just 1 over k squared. For the Newtonian potential, it's something more complicated, as we'll see. But in the periodic space, the Poisson equation Fourier space becomes particularly simple because the Green's function is actually analytic in k and very simple. So this is what we have to solve. The problem is we cannot have a fine enough mesh to represent the k vectors with large amplitude. These correspond to small scales. So what we can, however, do is we can make a force split like this, that we say, okay, let me define a long-range potential. I multiply these k modes here with an exponential cutoff on some scale, Rs. I can do this, and then I just define the complementary potential, the short-range potential, as the real potential minus this long-range one. So if I add these two potentials together, I end up with the correct potential again. So why do we do this? Well, when you now look at the long-range potential, you can say, oh, I can solve this now with the traditional particle mesh method. Because if I choose this cutoff scale such that it is sort of the order of the mesh size, then there are no smaller scale structures anymore in this potential, right? By smoothing off all the small scales here, I make this a perfectly well-defined problem that I can represent with a finite grid really accurately. So this is solvable by the traditional PM method, right? With, as we saw, with CIC mass assignment, FFTs, finite differencing, interpolation, and so on. But what do we do now with this? Basically, now we see formally what we actually have to do. If this is what we really get, if this is of the order of the mesh size, the traditional particle mesh method basically calculates something like this, except that they ignore the, a nice, well-defined smoothing here. They just leave this off to the grid, basically, to do the same thing. Effectively, the traditional particle mesh method does that, and the traditional p cubed m calculation tries to get an approximation to this by particle-particle summation on the scale of the cells. But now we can do better, right? We have an algebraically correct expression for this. Now let's Fourier transform this to real space. It turns out, if you do that, then you get this expression here. If you Fourier transform this back to real space, this short-range potential, you get actually minus gm over r, which is the Newtonian potential, but now multiplied with a cutoff function, which in this case is a complementary error function, r over 2rs. Now this complementary error function, as you'll see in a minute, this is unity on small scale. So if r is small against rs, it's just 1. And then for large scale, it suddenly makes a nosedive and drops really sharply to 0. Right? So this is a finite range gravity, what you have here, right, in real space. And this is the idea that we can solve this in the tree. So this is how this complementary error function looks like. We have this Newtonian potential modified with this thing. And just this shape factor here is unity. And then once you reach r over rs about unity, you see that suddenly the force drops very, very sharply. And what this means is that to calculate the short-range force, you only have to go out to maybe, say, 5 times rs. And beyond that, all the forces are negligible. Right? That means you can now say the short-range force is something that I have to calculate in a little ball of some radius rs around some coordinate. But the rest of the force will be delivered by the particle mesh scheme accurately. And I just then have to add these forces together. So the advantages of such a combined scheme is that you inherit now from the particle mesh scheme the very simple long-range force calculation that is perfectly accurate also for the large scales. And due to the force shaping, there's no force anisotropy left at the scale of the mesh cells. And also the speed is then insensitive to clustering because all the clustering stuff is now absorbed in the tree calculation. And the tree itself is also faster than it used to be because you only have to deal with this local neighborhood around the point in your tree calculation. And that's why this is a relatively efficient combination for especially cosmic structure formation calculation in the dark sector. Let me make a brief digression back to time integration, what I discussed this morning, because that will also relate to something I say later in the week about operator splitting. We saw this symplectic integration in the morning. And what is actually quite neat about this, you can also now use the splitting idea that we exploited for the force in a long-range and short-range potential and split the potential energies also in a short-range potential energy and a long-range potential energy. And now you see you have a separable Hamiltonian with 3 pieces. And again, you can employ the concepts of operator splitting to time integrate these pieces in a suitable alternating way. And for example, you can define a drift operator corresponding to this kinetic part and a kick operator to the short-range force and a kick operator to the long-range force. And you could then write your time evolution operator like this, that you say, okay, I'm first doing a half-step kick, say with my long-range part, this is this on the right. Now I need to evolve this piece, the short-range dynamics, over delta t. This is the whole square bracket here, raised to the m power. And then I need to finish off the time step by doing another half step for this piece of the Hamiltonian. But the evolution of this piece of the Hamiltonian you can now subcycle by some integer subdivision of the time step. Then you stay symplectic and you preserve the Hamiltonian characteristics of the system. Right? So this is directly suitable for the idea of operator splitting. And that makes such a force split scheme also, and this carries over also to other approaches like principle similarly to adaptive mesh refinement schemes, and as I said, I'll talk a little bit more about this later in the week. You can then have a relatively neat time integration scheme where it would just alternate. This sort of operator approach would just mean as the system drifts along, you can evolve the short-range dynamics, the short-range force, on a shorter time scale than the long-range force. which makes physically perfect sense. And this, however, with this sort of formalism, you also have this embedded in a nice Hamiltonian operator split. So there is a sound mathematical basis actually for doing this. So what this means is basically you would drift all the time by some small time step, and then only every once in a while you apply the long-range kick operator. This is the long-range force, and in between all the time you do the short-range gravitational force from the tree. And in a code you would then do, here you would do the Fourier transform business on long range, and here you would only in your little ball around, which is very localized, you would then do the short-range dynamics. So I have, I think, maybe 5 to 10 minutes left. Before I leave this topic of the tree algorithm and the octree, I want to just briefly mention that this is also something that is useful. This structure of the octree can be usefully exploited for parallelization and domain decomposition. I will talk more about parallelization on Friday, but since I'm now talking about the tree geometry, I think I should mention this just very briefly. So normally when we have a large system that we want to calculate with many computers, often the data is also so large that we can't copy it in all the computers. We can't hold the data and on all the machines. We need to distribute it. We want to avoid data replication. Then you normally do a domain decomposition that most commonly you divide the data somehow spatially, for example. That means, for example, you maybe make an orthogonal recursive bisection of space to chop this off in some more or less equally sized pieces. This subdivision is in itself a bit tricky because we'll determine how well the work is balanced, and especially if the number of pieces gets very large, it becomes an interesting issue in its own right, how to do this best. Now, many codes now resort to so-called space-filling curves to do this, and I want to show you this briefly. Here is a so-called Peano-Hilbert or Hilbert curve, and this is an interesting fractal curve that fills the square, or you can see this here. This little U-shaped curve is visiting, if you imagine that this box is subdivided in 4 areas, each of these areas once, so you're connecting them once, and this curve is not intersecting itself anywhere. Now you can create a finer curve of this type by imagining that you subdivide this by a factor of 2, all the cells, and then you take this same U and you rotate it. Here's this again. This is the same U again, just rotated by 90 degrees. And here's it again, replicated here as well, and here again rotated. And so you have again a space-filling curve that visits these 4 on 4 cells exactly once. Okay? And you see where this is heading, so we can subdivide again by having here, say, the 8 squared cell. And then you replicate this guy. Here's it again, etc. So you have self-similarity in this curve. And ad infinitum, basically. You can make this finer and finer and finer hierarchically in this fashion. So this has this curve is self-similar, and it has an interesting property that 2 points that are close in on the line, they will also be closed in 3D space. Okay, so it's a kind of an optimal mapping of the in this case, 2-dimensional space on a line where you try to maintain a lot of spatial coherence. That means that the information that 2 points are close together in 2D space is preserved to a large degree. And that is, for example, also used for ordering data in files or in memory and so on to make cache usage better, etc. But in the context of domain decompositions, you can now cut this space-filling curve at some arbitrary points, and then you create from it domain pieces. So for example, we have this string, this red line, and I cut it at four pieces here, at 4 places, and then the cells that are touched by this curve make up then topologically sort of convex domains that can be mapped, for example, to individual processes. So this is, for example, how we can exploit these space filling curves, and the power of two subdivision nature that's inherent here. That's the same subdivision, of course, that you have in the octree. In fact, if you employ this sort of Peano-Hilbert curve, and that's also possible to generalize this to 3D, then you will subdivide the octree, that is the fiducial octree for the global system, into disjoint pieces right at the boundaries and the natural boundaries of tree cells. Right? So you do not have to cut individual nodes into two pieces that way, but the tree that, the global tree that maybe never really exists on any of the computers because way too large, you will then give individual branches to individual domains without modifying these branches in any way. And that is also has many advantages, because you then can avoid that your algorithm is actually affected by the domains where they are placed, where they are cut. Right? This is then the forces are invariant with respect to this modulo round of errors when adding things together. So this is, for example, how the gadget code tries to do this. So any of these subdivisions of this Peano-Hilbert curve induces then a subdivision of the global Barnes and Hut octree. Okay, so this was a short digression to the issue of domain decomposition. So in principle, I could now say something about initial conditions generation. Should I do that, or should we move to the hands-on session? Let's make a poll here. Who's for lecture? Okay, that's not so many. Who's for hands-on stuff? Okay, the others don't care, I guess. Yeah, these are huh? What? Yeah, so yeah, let's see. I mean, to see how many slides these are. So these are another 10 slides. You want to hear those? Okay. Okay. All right, so just I try to make this relatively quick. So just two aspects of this initial conditions generation. What we often want is to create, say, prefabricated galaxy models. That's very useful to then, experiment with a galaxy, for example, colliding it with another one, or setting up, for example, a galaxy cluster, and you throw in a galaxy. You then and want to see what happens. You maybe want to try out new physics that you have thought about in an isolated setting. And for this, you would like to calculate models that are reasonable lookalikes for real galaxies in the universe. And here the task is to come up with a stable nonlinear object that has a plausible structure and that is in equilibrium normally. You would like to have it in more or less in equilibrium. The other completely different nature of initial conditions generation is creating basically almost constant density fields that are mildly perturbed, but just in the right way, that they are the real represent realizations of, say, a lambda CDM cosmology. So these are the cosmological initial conditions, and that's somewhat simpler, but in general also complicated if you want to be really careful with it. So, for example, if you want to have a static solution of the collisionist-Boltzmann equation, because that's what you're after if you're looking for example, a dark matter halo describing a galaxy, you really would like to have a static solution of the collisionist-Boltzmann equation. And there's quite a bit of theory about this. So there are, for example, theorems like Gene theorem that steady state solutions of the collision-Boltzmann equation only depend on integrals of motion. But, and these are very powerful theorems. An integral of motion is basically when some functional of the orbital elements, say x and v, x and the, say the coordinate and the velocity is constant along some along orbits. This can, for example, can be the energy, for example. Unfortunately, this theorem cannot be easily exploited in many cases. Only in spherically symmetric case, it can be very powerfully exploited, but not so much in any more general case. So in the spherical case, there you have good chances to be able to use that. And the related theory, for example, Eddington's formula. Here's an example, the Hörnquist halo. This is a density profile, three-dimensional density profile, and it's spherically symmetric. This, it's a bit like an NFW profile, except that it declines faster in the outside, and the mass is then finite. The question is, if you want a dark matter model exactly with this density profile, that if you put it as an n-body realization onto the computer and evolve it, that this is then stable in time. Right? This is basically what you would like to have. And in such a dark matter halo, you could then study, for example, an evolving galaxy disk, maybe. This is something you might want to do. How do you do this then in practice? How do you set up these initial conditions? Well, as far as the Hörnquist halo goes, you're lucky because that admits a solution, and even an analytic solution, to the distribution function, depending only on the energy. This is basically derived in a very complicated way with the Eddington formula. Even applying this formula is not entirely trivial. You can try it out to set up basically this mass density field and then the velocity distribution at every point described by this distribution function. So this can be in some rare cases. Well, you know, there are a few more of these pairs, density profile, distribution function pairs that are known, and you can use those sometimes with. And if this is available, then you should, because that's really the best way to construct a model. Often, however, you would like to have perfect freedom to choose whatever density you would like. And often you look at axisymmetric systems. Say you make a galaxy model with a stellar disk, stellar bulge, maybe a gaseous disk. Then you have an axisymmetric system, and maybe there's even a stand for supermassive black hole. You don't have the opportunity then to use analytic distribution functions anymore for this. You can then make such direct matter models. For example, you could describe, say, the dark matter profile with an NFW or a Hörnquist or a Moore profile or something like this. This would be strongly peaked towards the center. That would be your desired dark matter profile. You then maybe have a desired stellar profile, stars in the disk. Say most canonical choice will be an exponential surface density profile like this. A two-dimensional surface density is not enough for a three-dimensional model, right? So you have to actually extend this to 3 dimensions. Here the most common choice will be an isothermal sheet, and as you pretend that at every radius this behaves like an isothermal Spitzer isothermal sheet. This is the solution that you get if you imagine that there is an infinite sheet, and then the gravity is only is unidirectional, perpendicular to this sheet. It can be also analytically solved. You get then for an isothermal distribution this sec-squared density profile, which looks like sort of a more or less like a Gaussian in the vertical direction. This would be then a 3-dimensional extension of this that you just would like to have, say, in your model. And so on. So you then can add a bulge of some analytic density shape, or doesn't even have to be analytic, could also be tabulated, and some gas in the disk of some nature. For the gas, you know a little bit more. You have, for example, hydrostatic equilibrium, maybe in the vertical direction, through the pressure directly, which you could also exploit to construct an initial conditions model. Now, one approach that's very widely employed, which is, however, not extremely good, I would say, but sort of works, is to assume that the velocity distribution function for the dark matter and the stars at every point is well approximated by a triaxial Gaussian. I just assume that the collisionless components are locally behaving like I have a distribution function that, or velocity distribution function that's a triaxial Gaussian, and try to estimate now just the dispersions in all the 3 principal directions. And this you can do that very well in axisymmetric systems with the Jeans equations, because there you then know that certain cross moments between the velocity expectation values, say VR is in the radial direction, VZ, Z direction. If in a stationary system all of these cross moments and simple moments must vanish, and the radial and vertical moments are given by this Jeans equation. This is what you can derive this by taking just the collision-Boltzmann equation and the Poisson equation, integrating in various ways over them, building moments, etc. You get equations like these. These are called the Jeans equations, and that's something you can actually calculate, right? If the density is given, you know the potential, and you can do these line integrals through the force field multiplied with the density. And in this way, you can actually calculate all the second moments of the velocity distributions, and because you assumed that only those count, then you're basically done. Then you know the velocity distribution. And that's one way to create models that are approximately in equilibrium. If you do it like this, you will get a galaxy model in this case that is approximately in equilibrium. It's only approximately in equilibrium because the velocity distribution is actually not just this triaxial Gaussian. It's close to it sometimes, but it's usually slightly different. And so if you simulate this on the computer, the galaxy will, in the first dynamical time, also relax to a real equilibrium, which will be slightly different from what you put in, and you have little control about this. That's why this is not perfect. Okay, but so I think it's actually be a good idea to find something better here, which is in principle possible. The other types of initial conditions are cosmological initial conditions. So here we start essentially from observations of the initial state of the universe left behind after the Big Bang. And you know that this is seen, say, in the microwave background. We have the fluctuations. We have a good idea about the linear theory power spectrum. This is an old figure from Max Tegmark showing various probes. Here is the microwave background on very large scales. And then there are galaxy surveys, clusters, lensing, and on very small scales, the Lyman alpha forest. So I think, you know, it's remarkable. This one linear theory power spectrum, which is this concordance cosmology, can describe this data fairly well. Of course, you know, there's a lot of debate whether there are tilts and so on in here, but this is sort of the fine print. Overall, we know the power spectrum shape, the global one, very well, and we understand where the shape comes from. And this is the linear theory power spectrum, where all of these probes have been basically linearly evolved to the same epoch. And so the nonlinear evolution is basically not even on here. Now what we want to do is, we want to, in this cosmological initial condition, we want to create a realization of the density fluctuation field where maybe whatever, depending on what scales we want to simulate, where this linear theory power spectrum is expectedly imprinted at some high redshift. Right? And what only really matters for this, the shape of this power spectrum is determined. You cannot really see this there, but these baryonic acoustic oscillations, well, here a little bit, the wiggles are there. These are exploited in microwave background to determine cosmological parameters. The shape of this is basically only a function of cosmological parameters, and then in linear theory, this just slides up with time, you know, up and down with time in linear theory. But we don't have a theory for calculating anything about the amplitude. So this is a purely observational quantity at this point, the normalization of the power spectrum. So this is one of the most important things. How is this set? The normalization is just this mass fluctuations on the scale of 8 megaparsec done with this convolution integral. So suppose we have this normalization also. Then that means we have the shape of the power spectrum coming from the basic cosmology and the normalization, and we would like to create a realization of this power spectrum for an unperturbed universe. So the very first thing you need to do is to create yourself an unperturbed universe. An unperturbed universe is one with constant density. And if you do n-body dynamics, you have essentially, I mean, the most natural thing that I think everybody of you would do, including myself, would be use a grid like this. So a Cartesian grid is one realization of a model of constant density if you have a certain number of points. It has the disadvantage that it's fairly regular. There are preferred directions, which are the principal coordinate axes. Well, question is, does it matter or not? It's not so obvious that it matters, so we would like to probe that also with alternatives. One is, for example, using a glass. This is this distribution on the right. You see, this also looks kind of regular. This is not a random distribution. A random distribution would be that you throw the points randomly into your box. That is a so-called Poisson sampling. The power spectrum of this is flat. Okay, it's white noise. But there is a relatively large white noise everywhere. And by going to a glass, you create this by now evolving this random point set, which is very strongly clustered, with gravity reversed, the sign reversed, so that the points repel each other. And then they will settle after a while in such a, it's called glass-like structure. And that has no preferred directions. And it also has, on average, the particles like to settle into a structure where the mean separation to the neighbors is roughly the mean particle spacing, of course. But that is avoiding sort of the very sharp power that you have here at the mean particle spacing. It's spreading this a little bit more. And yeah, both is used in practice now. And both is a good model for an unperturbed universe, and you now have to perturb that unperturbed universe with your realization of the power spectrum. For this, you use the Seldovich approximation, right? How is that done? Well, you want to displace the particles from their Lagrangian coordinate. This is the initial coordinate in the unperturbed universe, say qi. And the displacement at some time is the current coordinate minus the initial coordinate. And you would like to calculate, if you can calculate this displacement at your initial time, then you just have to add it to the unperturbed coordinates, and you have your real initial coordinates, right? This is what we want to get. Now, the density change when you displace things like this, you can calculate from the Jacobian like this. So the density field, if you apply these displacements, would be the density field you have for the unperturbed coordinates. This is the constant density divided here by the Jacobian of this mapping. And this Jacobian, if the displacement is small, you can expand it, and it is something like 1 plus the divergence of this displacement field. So this you can relate to the density contrast. So the density contrast will then be minus the divergence of the displacement. And in linear growth, you can then realize that displacement will grow proportional to some initial displacement, d0 with time, with the growth factor, proportional also to the density fluctuation. So both of those things grow with the same factor in first order linear theory. Yeah, you can also put in the, express it like this, that the velocity x dot from these equations will be proportional to d. The particles will move also in the direction of the initial displacement. That means once you have the displacement field d, somehow we get to this, you also have the initial velocities. Yeah, and actually this growth factor, the d is the linear growth factor, the derivative, the logarithmic derivative with respect to a, this can be expressed again with cosmological parameters on the Hubble function, right? So we basically have that the velocities are something like the Hubble function times the displacement times this f of omega, which is about omega to the 0.6 power. Good approximation. How do you actually get the displacement field? This is essentially very simple. You can write down now the Poisson equation is the Laplacian for phi is proportional to the is the displacement, is the density fluctuation field. The displacement will be proportional to the forces, so it is proportional to minus gradient of phi. In this direction, you accelerate it. And then if you put this all together, you can then create a Fourier realization of the potential where all the modes are independent. And from this, you calculate displacement field and add it to all these particles. And the expectation value for all the different individual displacements are given by the power spectrum, right? So you basically draw random numbers from the power spectrum. Imaginary part and real parts are independent, and that gives actually a Rayleigh distribution function for the amplitude. So I mean, I in principle could say more about this, but it's, I think, relatively technical. But at one point I want to mention that is maybe not clear to all of you, is about the sampling theorem. So when you have, say, a box, periodic box of size L, you sample this with a certain number of points. I mean, I do it here in 2D, so if you have n squared points, you will often see in papers that people simulate whatever, 256 cube particles and so on. So the n would then be 256. So this is the particle number per linear dimension. And that basically means that you would have a grid of points in real space that is unperturbed, which then say 256 squared points in 2D like this. And then in Fourier space, this means that in Fourier space, the Fourier modes will have a spacing of 2 pi over L if you have a periodicity of on scale L. And the so-called Nyquist frequency, this is sort of illustrated with this blue shaded area here. The Nyquist frequency is the largest wave number that you can still sample with these points. You need a certain number of points to represent waves, right? If you go to higher k, you cannot represent with just 1 or 2. You cannot represent the corresponding sine and cosine waves with these 2 points. There would be aliasing of power. And in fact, in this blue region, out to the Nyquist frequency, if you count the number of independent modes, independent numbers, these numbers must exactly match the number of points you have here, because information will not be created or lost if you go to Fourier space. Right? So this is exactly the region where you have information in Fourier space if you have just these n squared sampling points in this box L. And that means if you create initial conditions, and we maybe do this in the exercises, you are not allowed to add waves all the way. If you just have n particles, you have to stop at a certain k. It's not possible to put in smaller scale perturbations because you have not enough sampling. If you do, nevertheless, you will alias this power towards larger scales, which is not good at all. Okay, so I think I'm at the end now, and let's maybe make 5 minutes break, and then we'll do this hands-on session for those of you who are interested in this.